टाइम फिक्स कर दिया, सैटरडे 5 बजे शाम को करते हैं, बट बिकॉज ऑफ योर कन्वीनियंस, क्योंकि तुम्हारे यहाँ 5 बजे बहुत जल्दी हो जाता है.
Yes, 5 o'clock means 4:30 in the morning. So.
4:30 in the morning, so we. That okay, let's do. Haji Siddharth, I think we should now start. People will be joining, all right? And once again you put and to our group, put one reminder that everybody should join. Aliam Tech, PhD.
All right. Sir, can we once check that if your slides are, presenting?
No. We are not.
It's been done, Anas. You can come.
Okay, it's been done. All right. Okay. Sir, should I start then, or we'll wait for some more time?
And I think let's start.
Okay.
Right.
So a very.
Prof. Singh, should we start now?
Yeah, I'm fine, sir. Yeah.
Let's start. People will join.
So a very good day to one and all present here, and a very warm welcome to the 32nd webinar series organized by the Food Chemistry and Technology Lab at IIT Kharagpur. Indeed, since the beginning of the webinar series, we have had alumni from our laboratory, not just from different parts of our country, but also from different parts of the world, grace these webinars with their very insightful and amazing talks. Today on this 32nd webinar series, we have with us another alumnus of FCTL, that is Dr. Chandra Singh. He from the Lethbridge College in Canada. So before I formally introduce Dr. Chandra Singh, I would like to ask our mentor, Professor N Mishra, sir, to kindly say a few words about him.
Yes, thank you, Anas. So it's really a pleasure for me to welcome Dr. Chandra Singh. In fact, I still recall him as a CB Singh, and my association with him, of course, in the department and whatever was there, that is there, but more bonding was in the MS hall. CB Singh, remember?
Yes, sir. Yes.
And in the MS hall, it was started that time. I was the first warden who established the hall, and CB Singh was the first hall president. All right?
Yes. Yeah.
And obviously, you know that when we are creating any institution, something, so in the beginning there are some goals. Sometimes even the connecting road was not made, some furniture. So they are, in fact, CB Singh used to come and he always supported and wholeheartedly. So that, and it was that bond which had made even now also CB Singh regularly we are in touch with each other. And just now we are talking about that at least he has taken, you see that 3 out of his 5 PDFs, 3 are from our institute, IIT Kharagpur, and 2 are from my group only. That right, what is her name?
Gayatri and
Bridges. All right, these 2. So let's, without any further delay, let's go ahead. And in fact, these are the few that is CB Singh, like persons, they are the leaders, and now that for others, they are source of inspiration. That's how a person, in fact, we know that as what is the background, coming from a village background, from UP, from Bada. I think you belong to Bada.
Yeah, Chitrakoot, sir. Yes.
Remember, so yeah. From that Chitrakoot Bada, from village background, and to reach to such a high level. And I'm very happy to say that he has made now his name in the field, in the talk about grain storage, right? CV Singh, people will tell CV Singh. You put in the Google grain storage, you will find his name. So that's, in fact, for us, we get pleasure in this, and when our student and our friends, they come to such popular, become popular, etc. Yes, Anas, thank you. We welcome once again,
Yes, sir.
CV Singh, and please go ahead.
Yes.
Yeah, thanks, Anas, for introduction.
Thank you very
and
much.
thank you, sir. Obviously,
Thank you.
from the MS Hall, things that in your mentorship I learned about the management, probably they are helping still me. And throughout my work in the industry, then I moved to faculty in Australia and back to the college where I'm setting up my own center here. But those things started in IIT Kharagpur. And yes, my background, I grew up in a very small farm in northern India, near Chitrakoot, with a population of 500 people, less than that, in very small farm town. And then did my engineering from JB Pant University and master's from IIT Kharagpur and PhD from University of Manitoba. I'm currently,
Thank you, sir.
yeah, so,
Yeah.
should I say my screen?
CV Singh, just Anas will formally, they have some little more formality.
Okay.
Yes, sir. Sir, thank you so much, Mishra sir, and also Chandra sir, for sharing this very inspirational story. And now I would like to formally introduce Dr. Chandra Singh to our audience. Dr. Chandra Singh is a professional engineer registered in Alberta. He completed his undergraduate degree in agricultural engineering from the GB Pant University of Agriculture and Technology, and his master's in post-harvest engineering from the Indian Institute of Technology, Kharagpur, both in India. He then moved to Canada and obtained his PhD in biosystems engineering from the University of Manitoba. His doctoral research was focused on detection of insect and fungal damage and incidence of sprouting in stored wheat using near-infrared hyperspectral and digital color imaging. He conducted postdoctoral research at the Canadian Wheat Port Centre for Grain Storage Research in Winnipeg. In his postdoctoral research, Dr. Singh used synchrotron-sourced infrared imaging to detect damage caused by molds in wheat and canola. Prior to assuming his current role of Applied Research Chair at the Lethbridge College, Dr. Singh was Associate Professor at the University of South Australia. Dr. Singh worked in industry for nearly 5 years as grain management expert and principal engineer in an international grain management technology company based in Calgary. He has several peer-reviewed publications from his research, which focuses on myriad topics in the area of post-harvest engineering and grain storage management. So with this, we are all very much excited to listen to Dr. Chandra B. Singh. So, sir, and I would now like to formally invite sir for his presentation.
Yeah. Thanks, Anas, for your kind introduction. So I'm going to share my screen now. And are you able to see it?
Yes, sir, yes.
Okay. Thank you. So I'm going to talk about in my presentation about smart grain management technology for long-term safe storage of grains. I'll start with my Advanced Post-Harvest Technology Center at the college where I conduct my research. I joined the college in 2019, more than a little over 2 years now. In last 2 years, I have been able to bring in, my group has been able to bring in more than $5 million from different grants and contracts for the center. And that also included a $2.4 million CFI funding to develop actually the center for all the infrastructure and lab equipment for the center. The center focuses on storability of local crops, grains, mainly wheat, barley, canola, the pulses. These are the major crops. Potato is another big crop here, and sugar beet. And the goal is to minimize the post-harvest losses of all these crops. We partner with local egg industry that includes tech companies, growers organizations, processors, and we work closely with them on different projects with their active participation. We deliver research outcomes through our extension programs. So we are working with these organizations and sharing our research results, outcomes with them so that they can reach to the farmers. And long-term goal for the center is to that we can scale up or down for this technology to reach to developing countries in near future. This is a brief overview of my talk. What is my research motivation? I'll talk about grain spoilage and how smart grain management technology can help. And the major part is grain monitoring, grain conditioning, which is drying and aeration, and the use of modeling in grain stored ecosystem, and then summary of my work. So my biggest motivation is that how we can contribute to feeding the
Excuse me, CV Singh, would you go to
Yes.
the presentation mode? Please go to the presentation mode.
How do I?
That full slide, you just, because full slide PPT is not being shown here.
So is that good, or you want me to?
Not it. It is the PowerPoint presentation, no? Go
Yes,
to the
yes,
slide,
yeah.
slide flow, slide show.
Okay.
उसका बगल में, हाँ, yes, that's there. So click on that.
Can you see, or is it still some issue? Yeah. Okay, let me. Okay, so I'm stopping here, sorry. So what should I do? Share the three options: entire screen, window, or tab?
Total screen, entire screen.
Okay.
You share entire screen.
Okay. Like this? But then. No?
Now, then you go to the presentation mode. Click there. Yes, now it's fine.
Yeah, okay. Okay. Can you see it now? Sorry.
Okay. Yeah. Now it's good.
Okay. So let's start here. And what is our research motivation? Is the big challenge the world is facing is to have enough food. Food security is a real issue. World population is expected to reach 9.8 billion by 2050 from the current $7.6 billion. And this data is a couple of years old, but it's still relevant. 50% increase in food production will be needed, according to FAO. So that means that there will be higher pressure on natural resources and sustainability of the food system. About 2.6 billion tons of grains are produced, but 10 to 30% losses occur, which could feed additional 1.35 billion people. So there's huge losses, and these losses occur during production, storage, handling, and processing. The challenges with stored grains ecosystem are manifold. We have condensation, respiration, sprout and mold, insect damage, birds, rodents, depend on your storage type in storage condition. So it's a complex environment, and that's what we have to deal with these issues to minimize the post-harvest losses. Grain spoilage results in weight, quality, nutrition, and seed viability losses. Molds in the grain may produce carcinogenic mycotoxins, making the grain unfit for the consumption. Insects cause significant post-harvest losses of about 9 to 20% in different parts of the world. Heat from respiration of grain and molds, including insects, may cause development of hot spots. So that may lead to significant spoilage in bulk storage conditions. This is some of the examples I mentioned. So that was a previous report from India. So like many other parts of the world, India also has storage issues, challenges. And you might sometimes notice or see if you are in that grain storage issue that these issues are still seen in India as well. Not just India. This is a story from Canada. Saskatchewan is a state or province here, and you can see that this bin with canola caught fire in 2016, I believe, due to the self-heating most likely. This is another bin, corn bin in Denison, Iowa, that also caught fire. So spoilage could happen even in a proper storage structure if it is not properly managed. So what happens if you look at this table? What it does is that in this, these are different, the columns are different moisture cables and temperature cables. They are suspended from the top of the bin inside, and you can see how the temperature increased. So these are indicated finite. That data is from US, one of the sites from the company, OP System I used to work with. And you can see that the temperature of the grain reached more than 60 degrees Celsius here. So this is how in the bulk storage, the self-heating of the grain can cause actually significant spoilage. And sometimes the fire, as you see, may result into the fire, as you saw in my two previous slides. So how do we store it safely? Safe storage refers to the storage of grain for longer periods without any significant spoilage. Stored grain changes physically and chemically. Temperature and grain moisture are the two most significant factors that determine the safe storage period of the grain. So these are managing temperature and moisture, like many perishable or other agriculture commodities. These are the two key management points that has to be considered. Immature and broken damaged kernels, unclean grain with fine material has relatively shorter safe storage period. It has high risk of spoilage due to mold insect infestation. Safe storage period is cumulative. So if you have stored already some grain in poor conditions without managing temperature moisture, then even if you treat the grain, its overall shelf life will be reduced. So sooner is better. As soon as you notice some problem, as soon as the crop is harvested, immediate some correction should be taken in terms of managing temperature and moisture or cleaning. So how we can do it? What smart grain management is? How we can do? So like it's all about how we are going to use the development or new innovation in digital world. So now this technology, you are able to use cloud-based monitoring, management, everything. So one part is the monitor. If you have the storage, grain storage, how you can remotely monitor, how you can store the data into cloud, modify. Once you have the input, your grain conditions, say high moisture, high temperature, how can you modify those conditions in stored grain ecosystem? By aerating, cooling the grain, or by drying the grain using in-bin drying, high temperature drying. And in some case, how you can treat. So for example, you notice high insect activity, how you can treat it. And all the information is compiled. All the information is visible into the supply chain. So not one person, but many people in that supply chain are able to see what is going on within the stored grain ecosystem. Modeling is a big part because you don't want to wait until you see some problem. So modeling can help you actually pre-plan everything. You can see what's going to happen, how long it can be, grain can be stored safely, how long it will take to dry it, how long it will take to cool it, how long it will take to maintain in those conditions, what will be the energy use. All these things now using cloud computing, web-based tools that you can do. You don't need any very sophisticated high computing tool to do it. They should be very easy, and any average user should be able to use this technology for managing or storing the grains. This is one grain bin, schematic of the grain bin that shows different sensors that are now part of the stored grain management, smart sensors. These blue cables, these are the one with the node is called temperature, moisture cables, and then other one is the temperature cables. And there are several of them. They are suspended from the top inside the grain bin. and they monitor grain moisture and temperature at different depths. So you can know the temperature and moisture of the grain in real time. Also, it has electronic insector. That device actually captures the insects, calculates the insects in each trap, and then estimates the density of insects in the whole bin. So you can know if there are insects and how critical the problem is. So that way you can make a decision whether you have to fumigate or not, rather than randomly fumigating. So sometimes there's not requirement, still you are fumigating. Sometimes there are insect problems, but if you cannot see the problem, then you are not taking right action at right time. Also, the headspace temperature RH sensor that gives you indication when the condensation could happen into the top. And this is very common here. Sometimes in the daytime, the bin is hot, so the headspace is hot inside. Nighttime, it's a metal surface that gets cooler faster in the nighttime, and from when the air inside hits the inner surface of this bin, and then that gets condensed on the surface and dropped on the grain, and then that moisture is absorbed by the grain, and that causes further spoilage. It has a local weather station, so you know not just the grain condition, you also know the outside condition, and this is very important. So to run an aeration fan, which is connected to the bin, if you see on the right side at the bottom, and that to make a smart decision, it has to be a closed loop system. So for example, you know the grain temperature, grain moisture. If the grain is hot, you have to look at the outside local condition. So you run the fan, or the system automatically runs the fan. When the outside is cooler. There's no point of running the fan if outside condition is hotter than the grain itself. Rather than cooling, it will you further warm your grain or create hot condition inside. It has also a plenum condition. So you know when the fan is running, the pressure is high. If, for example, you have any problem with the motor is not running and your system is still turning the fan on, this will notify you that there is some condition, some problem, because the sensor is not able to see any pressure increase due to the fan operation. So this is an example how a grain bin and all this data is visible to you from anywhere. You don't have to be near the bin. You don't have to be using a desktop computer. You can monitor remotely from anywhere using just a simple browser or cell phone. So this is a cloud-based grain management system here. On the left side, if you see that CN cable node, it's a solar power node on the top that's connected to the cables, the moisture, temperature, everything that's inside the grain bin, moisture cable, temperature cable, plenum, every bin data from this cable node is wirelessly communicated to gateway. And this gateway could be within 1 kilometer, ideally 700 to 800 meters. So if you have a farm with the grain bins and there's an office or any structure, you can put it near them. And that gateway actually is connected to your cellular modem. And that's how your data is from this gateway through the cellular modem is thrown into the cloud. And then you can access that data from the cloud from anywhere. Not only you can access that data, if you make a change, say you want to turn the fan on, so using your cell phone, you turn it on the fan, that information from the cloud will go to the gateway again, and then gateway will communicate. On the left side, you see the fan node, okay? Fan node radio. So again, it's all wireless. So gateway will communicate to fan node through the fan node radio, and that information from fan node is then used to make a decision whether to turn the fan on or not. And then fan node has all the inputs from the grain bin, weather station, and then that based on the logic or the condition that you have in your fan control, that decision will be made. And once that decision is made, fan is running, all that data through the fan node from the gateway, the cable node, is again through the gateway visible to you through the cloud, almost in real time, or a little bit of lag. This is the weather station that when I was in Australia, we were doing some erosion study in these grain bins, and we used this similar system to gather all the information from this 1,000-ton grain bin. I mentioned grain monitoring is very critical. Stored grain is always susceptible to spoilage due to self-heating, condensation, mold growth, and insect infestation. Monitoring of grain moisture, temperature, insect activity, CO2 level, and phosphine are vital to develop best grain management practices. If you have a spoiled grain, it's not just the increase in moisture and temperature, but also increased CO2 level activity. So we can also now use the CO2 sensor to monitor increased activity inside the stored grain system. Grain monitoring not only ensures safe storage, but also provides early warning. So if you see any increase, you don't have to wait for those bad conditions. Any temperature rise or rate of change of in temperature. So rate of change alarm. So if you have a system where it's monitoring the grain temperature in real time, and if there's any increase in temperature, then you get a text message, or you get an email, or you get alarm in the beeping in your system if you are using that in desktop. That tells you that your temperature is rising. And then you can make a decision. You can go inspect the bin, cool it, turn the fan on, and see what is the problem, what are the potential solutions that you have. Or the worst case, you can move the grain, sell it earlier rather than waiting and get more economical losses. Monitoring ensures the effectiveness of aeration fan control strategy. So in previous slide, I said that all the input from the grain bin is used in the smart fan control decision making based on the real grain conditions. So I showed that picture. This is the data from those bins, one of the bins, and location is in South Australia. When we loaded that grain bin, where it was, you can see barley with initial temperature as high as 36 degrees Celsius. So when the cycle is different, when we have winter time in North America or in India as their summertime. So when they harvest the grain, it's really hot. And if you look on this, your right side, these temperatures are perfect for actually insect activity. So over 25, around 30, 32 degrees Celsius, that's why the insects, their growth is almost exponential. So it's important to cool it. And then we use this system and then try to cool it down, brought it almost below 20. So below 20, their reproduction stops actually. So that's how you control. And if you're able to bring it to below 15, their almost reproduction freezes. However, the challenge is that Australia, during that time, where you can see here in January, they still have the high temperature almost in 30, 40s. So the system actually picked the time when ambient conditions were cooler than the outside. And that was mostly late in the night and early in the morning time to keep the grain cool. And we did not have to turn it on and off every day. The system will take care of it and run the fan as required, and the conditions are favorable. This is another data from a grain bin in one farmer. He shared that data to us that canola is a major oil seed crop in Canada. So, and this has very high oil content, that any oil seeds, more than 40%. That means it has high rate of respiration, so, and self-heating tendency. So when they harvested, the bin was loaded with all the canola here under 26 degrees Celsius. Within a week, that spiked to 30 degrees Celsius, 4 degrees high. By this time, if you have an automated system, that rate of change of anything over 3 degrees, you will be notified by text message that your canola is heating for some reason. So next 4 days from 30 to 40. So you see the spike. Once it starts heating, and then it reaches a point where it's beyond your control. So then at this time, they moved the canola. It was a small bin. And it was outside, was in January, it's probably minus 20 or something. So when they moved that outside in truck, unloaded all the canola, they cooled it down, and then they were able to store it until June and sold it as number one. So number one means that it's the highest grade, no penalty. You get the best price for your crop. So it's graded number 1, 2, 3, 4, 5. Anything below 2 is a huge loss. If it is 3 and 4, it has no food consumption uses. So it has to go into some different, or there's no value into the crop. So it's important to maintain the quality, maintain the grade to get the optimum value or the maximum value from the crop actually. This is another data is coming. If you recall those temperature sensors in the grain bin, suspended cables vertically and getting those sensor data at different depth or different layers of the grain here. So you can see again here, it's a rice bin out of US here. You can see the biggest spike here. And again, this data is degree Fahrenheit, but more than 60 degrees Celsius. So when they notice this increase, then they turn the fan on and then they try to cool it down to 60 degrees Fahrenheit, which is probably within 12, 13 degrees Celsius, and then kept it cooler during the storage time. This is another bin that you can see that all the green is almost 12 to 15 degrees Celsius, but red hot is more than 100 degrees Fahrenheit. So this is how the data, if you are able to see it, then you can take some corrective action, maintain, see what's going on. Otherwise, these are huge bins, 1,000 ton, 2,000 ton grain bins. Without any sensor data, you have zero visibility. You don't know. Sometimes people see when there's smoke, they see there's smoke coming out of the bin, but that's too late to do anything with that grain type. So when you have these conditions, the best way is to modify the stored grain ecosystem. And modifying means drying and aeration, conditioning the grain. So dry and cool grain is the key for long-term safe storage, as with many other crops. So is with the grains. A crop can be harvested as soon as it reaches physiological maturity and can be dried. So here the farms are very big. They don't have time to dry everything on farm. It's too late. It's mostly they harvest. We are getting into the winter. There will be snow. There will be rain. So they harvest early. So safe storage, for example, wheat is 14% here. If they can harvest at 18, put it into the bin and use the in-bin drying system to dry the grain, that's the best, and then store it before they sell in 68 months' time down the line. Another advantage is that when the crop is harvested, there's a lot of product in the market, like many commodities. So there's surplus, the price is low. So advantage of storing is that when the demand is more, supply is less, they get best price. So typically 6-month storage is better, gives you better return on your investments. In bin drying, it's low cost. You just run the fan and use the potential of natural air, dry and warm air to remove the moisture from your grain. Once you dry the grain, then keep it cooler. You can be aerated. The grain can be aerated. And North American condition, they have no problem. We are in the winter time. Temperature is really, really low. So 2 to 3 degrees Celsius, 5 degrees Celsius, you can cool. But depend different parts of the world. As I showed the example in Australia, it's not easy to cool it to 3 degrees, but it's still under 20. It's way better than storing at 35, 30 degrees Celsius. So will be for India. Anything if you can store below 15, that will be really good. That's the aeration data. I put in another slide now here. So these are different cables. You can see T1, M1 is the moisture cable that gives you the moisture in center. And this T2, T3, T4 as the temperature cable. And these not, you see these here, solid points. These are the sensor locations. So for example, if you look at on the right side, M1 is the moisture cable 1, and sensor 1 is the bottom, and all the way S9 is 36.2. So these ones are not solid, they are not in the grain. So also the system can actually determine which sensor is inside the grain, which is outside. So it knows. So if outside is too hot, don't have to worry, because the system knows that that's not in the grain. That's in the head space. The air is hotter, not the grain. So this with this bin, and what you can do that with this app, actually you can rotate 3D, visualize where is. So any sensor location, any problem, you can exactly pinpoint to that particular location where the problem is actually. Right size is the data. So November 20th, the data that was, the bin was filled. And this is on the left side is the, after the aeration on January 20th, that screen capture was taken from the site. There are different ways this, if you use this app, that you can see the 2D plots, any change in temperature, 3D view. Also, it gives you alarms. The alarms means there's something wrong with your fan or with the grain itself. If the fan is running, it shows you status, local weather. It's linked to the local weather system that gives you all the information, ambient moisture, average grain moisture, ambient temperature, max grain temperature. So all this information you can see from anywhere. In fact, when we did it at that time, I was in Canada, but my student who was working, a PhD student on this project, he was there, but I was remotely able to see, log in this data sitting here in Calgary. And the grain bin actually was in South Australia. So I said 2D. This is how you can see. These are different sensors that, that how the over the time, the solid is the when the fan is running. You can see the number of fan hours, so 414 hours of the total fan run time. That's how you can calculate the energy uses. And you can see how this started with very high temperature and how this cooling front slowly moving up. So you can see the red one is the bottom sensor. It started to cool down, and then the cooling front move up, second sensor, third sensor, four sensors, and how you can cool the grain down to almost 20. The fluctuating line is the solid, light blue is the weather ambient condition, ambient weather. So you see the fan when mostly the grain is the warmer than the ambient condition, then the fan was running here. So this gives you the idea how the aeration system works. This is another data from the rough rice drying, or the paddy, you call it paddy. This is drying of paddy in a grain bin in Australia. They had loaded the grain with almost up to 20% moisture. And over the period, you can see that all the sensor one, the bottom dried first, the drying front move up, second layer dried, third layer, fourth, fifth, and the final, and all was dried about 13.5 to 14% moisture content. And that's optimum for milling, that's optimum for the storage, long-term storage. So this is an example how you can efficiently dry your grain using in-bin aeration system without using any heat. That's the data from the same. So you can visualize your data like here in the 2D plot. Also, you can look the data for different, it's a huge bin. So it has many more cables, 18 cables, but you can see each cable, moisture is so uniform. Almost everything would be 13 to 0.5 to 14. So if you don't have a good system, you can over dry, no value. So this is a system where we did not have automated fan control. It's just manual. Turn the fan on, leave it, let it do whatever it can. In that condition, 12.4% is their lowest moisture. So it's a loss of 1.5%. So because the grain is traded based on the weight. So if you have a 1,000-ton bin, 1% moisture loss is a lot. So that's how it's not only energy efficiency or cooling and drying, it also you manage the moisture in a way that you don't lose the money. If you over dry, that's a loss for any farmer. This is our one of the interesting current projects. We have project that we are doing actually on-farm energy efficiency drawing across the Alberta. You can see here that one of the farm, it's a huge farm. They have over 14,000 acres of production. And this is the farmer. We visited this farm last summer. He is a mining engineer by training, but he decided to go back to his family farm, and he's managing these operations, fully automated system here for the drying, storage, everything. And Lethbridge College at the bottom. That farm is on the way up on the north side. So it's about 15 hours drive from here, our college. And we spend 1 week, and these are different locations where we have actually farmers. They're partnering with us to do these studies and monitor the energy uses, their drying system, their storage condition, what crop they are storing, how long they are storing, what are their costs of drying, what type of drying they use. All those information in that project we are collecting across the Alberta. And the goal is to come up with a recommendation to improve energy efficiency, reduce the drying costs, and increase the storability and quality of the wheat. That's the focus of this project. So, and I mentioned that mathematical modeling is very critical for stored grain ecosystem studies. These are the big wins. So any experiment that you want to try in a 1,000-ton bin, you can imagine if you have wheat in a 1,000-ton bin, that's around say $250 or $230 per ton, and you can multiply. It's at least 200,000 ton in each bin. So that's a huge risk. If you do some experiment and something goes wrong, you are risking a lot of money. Simulation can help you actually see what's going to happen in those conditions. So you don't have to experiment first before you actually see using the modeling. And then you do the validation to reduce the risk using the sensing technology to monitor it. So it's a very critical part of here. So modeling is not something new in this area as well. What is lacking is a comprehensive modeling approach, considering local condition, geographical location, structure type, what type of structure, what commodity you are storing, how long it has been stored, and what are the local factors involved in storing those commodities, including local weather, moisture, temperature, insect, molds. So for example, in Canada, insect is not a problem because we are in a cooler climate, but mold is a problem because you have high moisture grain and we have cooler condition for condensation. So it's a big risk to molds. Move other parts in India, maybe insect is a big problem. So is with other tropical countries where the warm climate, the insect population just explodes. Consider in a modeling, not only when you run the fan, when you are not doing anything, but the grain, as it has a tendency of self-heating, what will happen, how you model those conditions. So these are the things that should be considered. And I showed you in the beginning that stored grain ecosystem is very complex. So what we are trying to do is that you're working with these farmers, or research that we are trying with these companies to develop actually web-based tools which are easy to use and easy to interpret by users, particularly the farmers. Obviously, farmers here, they are much more advanced. They understand the technology. They understand the scale of that work that they are doing. But their goal is to reach it to the end user where they can simply use it, get some information to improve their storability or management of the crops. So within the modeling, computational food dynamics is playing a critical role in this. And it's a modeling tool to develop robust and flexible mathematical analysis of heat and moisture transfer occurring during the aeration process. This is based on finite volume methods. So airflow is a critical. How you change this, alter these conditions inside the grain is by moving the air. So modeling of airflow using finite volume method is very handy, very easy tool. It gives you accurate results that represent the inherent fluid flow properties, and you can relate it with thermophysical transfer phenomena and then model out the output conditions, as also in this here. CFT can be used to investigate the effects of geometry and location of aeration system. Also in a slide, what should be the ideal aeration system in a structure. Also investigate the degree of cooling or drying. Obviously, once you know the airflow, you know what it's going to do to the, and not just the airflow, but also its thermophysical condition properties and how it's going to alter the stored grain ecosystem. Ultimately, you are able to estimate what is the cost of doing that alteration or modifying the grain condition. If the cost is too high, then maybe it's not the best way to do it. So these are the things that modeling can be actually used. This is the brief overview of the finite volume method. You can use these are the mesh that you can divide the whole structure into a smaller section. They are called mesh here. In our study, one of my students, he worked on this project. He created this tetrahedral mesh on this cone section because of the shape of the grain is not uniform. It forms a cone due to the certain angle of repose. So he used a linear tetrahedral element size for that cone section and in the head space, and then hexahedral element for this more uniform area, and then use the mathematical models to create those partial differential equation, use finite volume method to discretely raise equations, and then have some solution methods, different solution methods, then converse them to find optimum solution. And then that included his work actually optimize element size, optimize solution methods, optimize time steps. He used the ANSYS software. If you are familiar, there are many options that you can do. So in this bin, actually, he created the optimum for this is a 1,000-ton bin. And it's a lot of computation. You can imagine that the optimum node size was more than 52,000. That was the node size with elements. So these are the nodes, and each side is considered as an element with over 293,000 elements. A huge computational burden, but now you are able to do it very fast. Using that modeling approach, you can see here that we can model the airflow distribution here. So you can see in the top static pressure as well as the airflow rate. So you see that the dead zone or dead spot, the darker blue areas, the darker it is in the scale, there's no airflow rate that the modeling can show you here. No airflow rate means that even if you're running the fan continuously or whatever system you use to cool it, there's no air that's going to go through this top solid area in the peak and the core. So is on the side. So that means that there's a high risk of spoilage here at the top because air is not going to alter any of those conditions in terms of temperature and humidity or the grain moisture. So this helps you know how we can identify whether our aeration system is sufficient. So once you know that, what do? You unload some of the grain. So either unload or then make the grain labeled. So why there's no airflow? Because it's a peaked grain. So air takes the path of least resistance. So moving through the sides, as you can see here, way more airflow, much more higher airflow rate through the side of the bin rather than center, because the depth of the grain is less, so resistance is less. We did that validation here. So when we modeled that, we went inside the bin, and it has oats as a grain it has, and then barley in the next year, I believe. there was almost zero airflow. We could not measure anything. And as you moved from center toward the side, the airflow increased. And this is how we validated the model. So in element size, this is very important in this case for the CFD modeling. What in this we did that we use a different strategy for the mesh size. We did not use the same mesh size here. The blues here, the shed here at the bottom, those are the areas and ducts connected to the fan outside. If you look on the left side, that's at the bottom is the fan. So, so the fan is at the bottom here, and that's the ducts are inside, and that's how the air is moved from the fan inside. So we had a finer mesh size here to make sure that we are capturing the information. We have quality mesh size, and then it ensures that the airflow distribution is near practical. Same thing outlet. So air moves through the bin from the bottom all the way to the up. And then also the top grain surface, it has a different grain shape, the cone. So we use define a different mesh strategy for here to ensure that we capture the information, all the variables inside. And there are two types. One is the flat bottom large bin, the top one, 1,000-ton silo, and the bottom one is smaller, 100-ton silo. It's hopper bottom, you can see here. So this one, the top one, has to be loaded through unload auger. In this bin, the unloading is done through the gravity. You just open the bottom opening funnel and then gate, and then the grain will flow through it. These bins are loaded from the top, if you can see here. So there's a loading auger that puts directly from the truck. We bring in, have the unload auger. Both the bins are loaded from the top, from the center. So this is the outcome. Once you are able to model the airflow distribution or the airflow, once you quantify the amount of air flowing in per minute, per second, per hour, you know the quality of air, you know the grain condition, the porosity, and everything is involved in the simulation. And then you can model. So these are the examples, initial conditions, and what will happen after a certain period of running the fan at different ambient air conditions. So in this case, it is the profile after 48 hours of runtime. So with that, this is my summary. Post-harvest grain losses can be significantly reduced by smart grain management technology. Grain handlers can make informed decisions to avail the best marketing opportunities. Once you know that your grain is good enough, safe enough for long-term storage, and you're not worried about any quality or spoilage loss, you can look for the best market. When you see the good market condition, you can sell the grain. Also, this efficient grain management means increased profitability through quality optimization, moisture control, energy savings, reduce operating costs, detection of contaminants, and prevention of spoilage. So this technology can help you in all these aspects. I'd like to thank my funding partners. We actively participated or received the funding from these companies to do my research in grains, potatoes, sugar beets. I'd also like to thank my collaborators. These are different collaborators that we work in different projects at the moment. Thank you.
Very interesting talk, Dr. C.V. Singh. I am sure there must be a lot of questions to Dr. Singh.
Yeah, sure. Yeah, well, we'll be very happy.
Yeah.
So there is a question by Ridesh sir. He's asking, what will be your suggestions for developing grain systems in India?
So India is moving in that direction, to my knowledge, that it's a different system in India. The farmers, they actually sell to FCI, Food Corporation, or different state warehousing. They store. So this is moving. This is not solution for on-farm storage in India. Most of my parents, they are farm. We have a small farm. This cost is very high. But when it moved in India, losses are most of the farmers they harvest, they sell right away to FCI. I think it's FCI food. So they have different warehouses. They sell it to them, and they store in their warehouses. So this is a viable solution. And I think the government of India, they are creating many hubs where they have actually 12,500 ton storage bins. I gave an example of 1,000 ton. If you have storage of 12,500 ton grains, each bin that's the capacity. And I was involved actually one of the warehousing projects from MP government. They have 10 sites. So they have 10 sites, 50,000 ton storage by MP government of wheat. It's done by Adani for them, Adani Agro. So this is how it's moving into India. I'm glad they have a requirement that there has to be temperature cables in those bins, but that's it. There are not yet established guidelines how to store. This could be a new research area. There will be job opportunities coming in India in that area if you are a grain management expert. I've been there. I've given training to Adani. I've been there, talked to the GSI, was one of the American grain bin manufacturing companies. That's an area. So solutions are very similar. Even I'm concerned about the scale that they are storing in 12,500 ton bins. They are huge. Anything that happens in those bins, it's a huge loss. Not to the farmer, but the handlers. So for example, if Adani is doing, or they have a big storage facility in Moga, I believe in Punjab, and this is moving in India. And I think recently I read an article, and many of you may have that information more than what I do, that they want to move and make it, I think, up to 10 million metric ton storage in those bin. And no doubt this storing in the grain bin is the best way of storing the grain. There's input cost, investment involved, but long-term storage, nothing will go wrong in 25, 30 years. And that's a big return on the investment, given the risk that you have for the grain.
Thank you, sir, for the answer. We have another question by Dushyant. He asks, how do we decide sensor positions in bins, sir?
So that's a good question. So grain itself is a poor heat conductor. So if something happened in one location, it's a very slow progression to the next, to the nearest location. So that's a tricky part. If you increase more sensors, the cost will increase of those cables. And also you need many cables in large bins. So for example, in that 12,500 ton bins, they are in 105 feet diameter bin, if I recall them, 120 feet diameter. So you need about 25, 30 cables. Then those cables are suspended from the top. So there is a load on the roof. You don't want to pull down the whole structure by additional load. And there is when you unload the bin, there is a friction on those bins, the cables, and that not the weight of the cable itself, but the friction and the load when you start unloading, that's caused. So these companies have come up with the standardized pattern. When you get a quote from a company, for example, I was working with the OPI, and they have a software where you give the bin information, where your bin diameter is 48 feet, 36 feet, or 60 or 100 feet. And then it gives you a spatial pattern. In general, the spacing is 6 feet is a standard. So one layer, next layer is 6 feet, next layer 6 feet. And what happens that anything in between, when you run the fan on, and that warm air moves up. So it's picked by the next sensor. So that's the best way that have at least 6 feet spacing. And most of the companies work around that number.
Thank you, sir. We also have questions from Sneha Chabra. She asks, how do we calibrate these sensors to ensure that they are providing correct information?
Yes, that's a very good question, actually. So temperature, they come with plus minus 0.5 degrees Celsius. So they are digital advanced sensor, commercial sensors. It's the same sensor used in all the medical devices or other applications. Moisture, many of you know who work in the grain on this area, grain isotherm curves. It's called also EMC curve, equilibrium moisture content. So that's where you need to do the calibration. There are different equations that you develop those accurate grain isotherm curves, and then the sensor, they don't measure direct moisture, so they measure temperature and humidity, and then convert into the moisture using those isotherm equations to accurate moisture. So your reference, how you reference, are you using an IR analyzer? Are you using your oven dry? What are you standard you are using? Are you using ASAB standard? So if your reference is accurate, then and your process is correct, and you develop those isotherm equations, and that's how you measure the moisture.
Thank you, sir, again for your very informative answer. We also have questions from Sakshi and Dushant. Can you, would you like to ask yourselves, Sakshi and Dushant?
Sure, sir.
Yes, please. Yeah, you can ask here. You don't have to type.
Good evening, sir. Sir, actually, I was asking, are these sensors able to detect the microorganisms before spoilage? Like after spoilage, that heating and temperature rise will take place. So, is there any way that they can detect the microorganism itself, and we can stop the spoilage before only?
No, Sakshi, they don't have capacity. They are simple temperature moisture, but based on experience from my own experience, the increase in respiration is way earlier than you notice any change into when you see the physical model. First stage is increasing. So if the grain has high moisture, it will start self-heating, respiration. When you have the heat of respiration, then there will be additional moisture. When that additional moisture and heating, then that will come to the development of molds, and then that's how will lead to the mycotoxin. And then once they are mold, then there will be sharp increase. So if you have the system and you are tracking it, before there's any significant portion of mold that you see or any mycotoxin, that increased indication will tell you way ahead of time, and you make sure that you cool it, dry it, and hopefully you don't have to see any molds problem in the grain.
Okay, sir. And sir, one more question, like these sensors might be having some range of working, like some distance of working. So, sir, how do we choose these, and like what are the ranges that you go for considering the bins for 120 feet?
Yeah, so the sensor, they are calibrated. They are commercial sensors. Many companies they make. The best one is Sensorion out of Switzerland. Honeywell, they have a lot of sensors for medical equipments. They make it. So indoor, outdoor sensor, temperature digital sensors, they have accuracy of within 0.5. My experiences with those sensors. Humidity sensor, they are within 2% up to say around 40% RH to 80% RH. On both the side, then their tolerance is a bit low. They go up to plus minus 3. So that's the limit. But if you convert that 2% into moisture, that tolerance will be say 1.5 to 1% moisture. So if you do oven dry test or you use an IR moisture meter, if you are getting 14%, sensor should be able to tell plus minus from 13 to 15. So still you are very close. You know what the grain conditions are. It's not that the grain is sitting at 18 and you are still getting the reading 14. And obviously your grain isotherm equations play a big role into it. So if you have a good sensor and you have good calibrated your grain isotherm equations, that you can use Austin equation, Chang Prost, the different equation, Henderson, that you can look for the data to optimize that accuracy, and they work pretty well.
Okay, sir. Thank you, sir.
So we have more questions actually,
Yes,
but also I had this one question before I move on to the questions of other participants. Like you mentioned, the different positions at which the grain temperatures are measured, And then
Yes.
based on that, those temperatures, the fan gets automatic, as in signal to act as an actuator to control those temperatures. Now, do we have any critical points in there, such as cold point, etc., based on which the fan decides, or is it like an average of all the temperatures?
Yeah, that's a very good question actually, and I happened to actually develop one control for the company. When I was there. So there's a minimum in where I am now. Maybe the temperature was -10 in the night. Today, I'm talking about today. Even it might be still negative, -2 or -3. So you don't want to run the fan because you are going to freeze the vents or the inlet of the fan or exhaust. So there's no point of using the air when below 0 degree. So there's a self check. It checks whether you can set any minimum temperature, 2, 5, -10 or 0. So you set up a minimum temperature. It takes care of that. It also looks at the maximum temperature. So anything over 30, you don't want to run the fan, no value. It checks that. Okay? It also looks that within the grain, what is the maximum? So anytime you set, say, my grain, my critical point is 30 degrees Celsius. If anytime grain is 30 degrees Celsius, your fan will automatically fire, no matter what outside, because 30 is extreme. You need to push the air through it. So those are different things that you can make a fan control decision based on the grain condition outside and your grain management practice.
Thank you, sir, for the answer. We also have one question from Dushant, that is, can we decide the sensor position based on CFD model we generated?
You can decide, but the limitation is the load on the cables. So that's a big factor, and the cost of the cables. So ideally, I would like to see every half a meter, but that's not realistic if you have a 12,500 ton. And there have been cases where due to the load, so a crop like rice, the rough rice, if you are storing, and then that rough rice had higher friction coefficient. So when you start unloading, that will definitely bring down the cable. It has a high risk that bringing them down. So we want to minimize the cable, but also not minimize, but optimize where we don't miss any location it goes unnoticed. So yes, we can use CFT, but that limitation will come from the cost of the cables and the load on those cables on the bin roof itself.
Thank you, sir, again for the answer. And we have a final question by Suryansh, who asks that in Canada, the variations in temperatures are low, but in India, it varies from 45 in summer to 17 in winter. So which may create instability in the system. And how do we tackle that problem?
That's a big challenge in India or any tropical countries like in Australia. So I showed my data. I think India, you will have to have the same approach. You challenge with the summer crop that you harvest in northern India. In April, May, that's when you harvest the grain, and then June, and that's the hottest months. So in certain area, you just peak that time. Keep it cooler. So you may not be able to cool immediately, but maybe July, I guess that's when you have a little bit more cooler window to cool it. Then you can operate more fan. And by then you move into the winter, then that will not be an issue. You can cool it to 10 or 5 degrees in some areas.
Okay, CV Singh, it's an excellent presentation. I have one just out of my curiosity. Okay, this is a very good system, and you are talking and in the on-farm storage for big farms, etc. That is good. But you see, in our country, in India, there are the farms holdings are very less farmers, and even in villages also the grain is stored, but it's in household in homes, but the storage size is less. So what I was thinking, what will be the problems? What are the potentials of developing a tailor-made or that is in-home smart grain storage facility like that? If you can come up with 1,000 kg or 5,000 kg facility, some such a smart storage system some company can make. So I am sure that there must be a lot of market in the country, but what will be the other problems? And it may be one very good thing that to control the growing spoilage, because in the FCI and government, etc., they are doing at the large scale, that is in no problem. But at a home scale storage in village level, can it not be done? What is your view?
Yeah, so actually I did think about it. There are two ways that the one is the cooperative models, where each farm, each village, they have a cooperative model. They have one bin, not 1,000 ton, but maybe 100 or 200 ton. That's probably say each farmer has 10 ton of the grain. So 10 farmers, so 20 farmers, they combine their grain and they make these relatively smaller bin, but same concept, same technology. And what they can do, because in India, they can use a lot of solar power. So it's a lot of farms, they will not have power maybe in capacity. So they can run these smaller fan with the solar power. Same system with the solar tech. So one is the cooperative model that they can use and combine the 10 or 20 or maybe a village labels and then store that all together. But I don't know, practicality will be a challenge on that side. That's one way. Like somebody brings in poor grain, or how they decide how many tons who has, and there's a theft issue. Obviously, you can have the camera, you can see, but then who is in charge? People might steal it. You can lock it still. So there are theft issue or those things. Or they at each farmers, they can be provided with 1,000 ton. The government can come up with at the panchayat level, where they give actually 1,000 ton, not 1,000, 1 ton or 2 ton small silos, steel structures, and have a fan, a small fan, one sensor, a small fan, and give them a solar panel, a small panel, and then they can store on their own. So it will be still costly, but given if they come up with that plan, and maybe so you can recommend that they give it to subsidizer, and that will be a big help. There are many things that government subsidize.
Is that available? That the system, that design? Etc.?
No, it's not. It's not. Yeah, but if the government takes that initiative, then
at least why don't you take up this project? At least being the situations in India now. So just decide that like 500 kg or what you tell, 5 ton or 10 ton is tarah se. Because cooperative model, what you are telling, that is, yes, it may work like a cold storage facility, and they can, but it will be better if you have a small size, that is just a smaller 500 kg or 1,000 kg grains can be kept in that, and each system is equipped with a small sensor and heating facility, and all these. Nowadays every village has electricity, so that can be even. Maybe initial cost may be a little bit high, but once the people get the advantage of it, they will try it, follow it. Of course, government, but we can talk to the government, but provided when there is a system, there is a design, etc., then definitely we can take it up.
And fumigation, I saw last time when there was a big conference on control atmospheric storage that in Delhi. I'm not sure you came or not. And then some people went, and the fumigation is not effective when you are storing in the bags. So with that 1,000 kg, I'm telling that you just put one tablet at the bottom and then let it go up, insect control. And with the bag storage, my own family, for example, that typical storage is in 100 kg jute bag, put the grain, it's sitting somewhere. It has no protection from ambient conditions. It gets hotter, insect can crawl in any time. And the big thing is the moisture. In June and July, August, when this rainy season, it's very humid and the grain absorbs moisture. So that creates a problem.
आप देखो ना, सिंपल इवन इंडिया में FCI इत्यादि जैसे ऑर्गेनाइजेशन से कैसे ग्रेन को स्टोर करते हैं, खरीद देते हैं, और मतलब पूरा स्टॉक सड़ जाता है और बाहर पानी में, बारिश में, सब जगह बिकता रहता है.
So here with this type of system, the losses are within 3%. 2 to 3% is the maximum.
I think
with these systems.
you should take up a small project on this, that is develop a smart, that is the user friendly, that is for village level, home level, a smart storage system, a smart growth and storage system.
And if government comes up with subsidy, I don't think it will
I
be that.
I think once the system is available, definitely government will come. That is the only thing. One has to approach the government and convince them. And I'm sure, but now the government is very proactive, farmer active, farmer friendly. They will definitely go in. But the system should be available.
Well, it will be very helpful, because right now the farmers, one thing is that they directly sell the grain. They don't have enough cash, so they want cash. But also they know there is a risk, they cannot store it. So if they know that in 4 to 6 months they will get better price, they will store it.
नहीं, अभी भी गांव में भाई हम लोग क्या गांव में तो स्टोर करते हैं, पुठला है, हंडी है, मिट्टी का लोग बना के रखते हैं. अगर इस तरह के हमें स्टोरेज फैसिलिटी मिलेगी, पीपल विल गो फॉर इट. That's good. Very nice. Yes. आप थोड़ा सा डिस्कस करो इसको अपने प्रोफेसर, क्या नाम है अपने गुरुजी से भी.
डॉक्टर जायस.
हाँ, डॉक्टर जायस से भी डिस्कस करो, बिकॉज इफ आप और डॉक्टर जायस दोनों लोगों की तरफ से अगर इस तरह से कुछ आता है, तो आई एम श्योर इंडिया गवर्नमेंट डेफिनेटली विल गिव दे विल कंसीडर इट.
And here I work with a lot of these grain manufacturers, bean company directly. They may not be directly involved, but anything design wise or the cost wise thing.
नहीं, आप एक डिजाइन करा के थोड़ा सा छोटा सा वहां पर फैब्रिकेट करा के get it tested, and once you are sure that it is working, and of course it should be not very costly.
I have one. I do have one.
Economical होना चाहिए, not very costly.
Okay, I have. If you allow me 1 minute, I'll share one of my presentations. Okay, you just give me 1 minute, sir.
Yes, sure.
Yeah.
Meantime, hello, Adra Gunasekaran is there. I find.
Yes, I'm okay.
Adra, how are you? Are you also working in the grain science?
No, sir, I was just interested in the presentation, so I joined.
Oh, very good, very good. So I think they are looking forward to hear you also sometime.
Okay, sir.
Have someone contacted you?
No, sir.
Not yet. So they will contact you. All right?
Okay.
Be ready for giving a similar presentation soon.
Okay, sir.
Okay. Proceed. Batao.
Yeah, are you able to see my screen?
Yes, sure.
Yeah, so this is actually 50 ton. no, not 50 ton, it's 50 bushel bin. So this is a small plastic bin that we have in our lab. So this is one model. Actually, we have it in our lab, and it has everything. We were doing some CO2 testing, so it has a moisture cable sensor, everything in this piece that we have.
So similar, if you get it made for steel.
Yeah, that will be cheaper. Yeah, that should be cheaper than this.
That will be definitely cheaper.
Yeah.
कितना approximately कितना cost आएगा एक bin का? Any idea?
It's very hard to say, sir, because here labor cost is very high. I'm sure it will be way more.
आप Indian labor cost consider करके बताओ. You know the Indian condition also. Approximately, obviously.
I'm not sure. It was very expensive. We paid $1,000 for something for this.
$1,000.
Yeah, but anything under 10,000 rupees should be the ideal. I don't know. Steel price is very high now, but even 10,000-20,000 for the whole structure and subsidized by government.
Agar 10,000-20,000 rupees jata for this structure, I think it may not be a problem. People now farmers are there; they will go for it definitely. If it is
Exactly,
available, you will buy it.
Yeah.
क्योंकि 10-20 हजार रुपया तो इस तरह के स्ट्रक्चर के लिए उतना तो एक बार में निकल जाएगा, एक साल की सेविंग में निकल जाएगा. Yes, Zakir, you want to say something? Zakir and Hridesh?
Yes, sir. Actually, sir, grains का तो ठीक है. Can we have similar type of structure for small quantity of apples? I mean, around 200 kgs, 300 kgs.
He's from Kashmir, so he has the Kashmir apple के लिए he wants.
It can be used. We are using the same for sugar beet storage, but that's in big bulk storage. It's again the cost. If you have
atmosphere को control करना पड़ेगा, not only temperature, you have to CO2, O2 also, O2 and CO2. It can be done, but you have to have O2 CO2 system.
Yes, sir. Yes, sir. Yes.
So less is the amount of storage, the cost will go very high. That's the big answer. And in India, one thing is that even with the same structure, because every farmer is small farm, like my parents, they don't have one crop. They have wheat or sometimes rice or beans, something. You can divide in the same structure, have two structures, so that same find two structures, but you store two crops into the same structure.
Multiple grain, multiple cover can be.
Yes.
It will be another good, very good thing.
Yeah.
In fact, you should work. काम करो, बताओ, then this can we can. एक बार अगर system है, when you come next time, then बताओ तो we can take it to the government, even food processing industry or FCI. अभी हमारा तो this rice fortification project में now FCI के साथ में हम लोग कुछ काम कर रहे हैं. If you provide some details of the system, we can discuss it with the Ministry of Food as well as the FCI also.
Yeah, I had a meeting with them in 2014 actually with the company that I used to work in India. That time they mentioned that they have a pilot. So that the bin system is right now is for wheat. I don't know, it might have changed, but they wanted to try it in 5,000 ton bushel bins for the paddy storage at that time. But then I left the company and questions. Yeah, I'm glad that people have questions and they have interest, because grain is not very interesting topic. If you look at it, people think it's very simple, no issue, but it's I'm very passionate, and last 10 years I have been mainly my life has been with the grains in very good success in that.
Still, आप चाहे जो भी कर लो, 10-15% तो on an average loss हो जाता है grain में भी.
Yeah, that's a lot. 15% is a lot.
Loss. And insect infestation इत्यादि के लिए.
Yeah. And also a lot of, I did not bring in that, but the grain safety, food
How
quality
is that?
safety,
All those things.
no, here there's a regulation. So mycotoxin, very low tolerance for mycotoxins. But in India, when they produce the grain, they leave it at the farm. If there is a mold and they feed the cows, and that mycotoxin then comes into the human. Cancer is a major health issue in India, and the reason is there's no regulation, no awareness for the food safety across the supply chain. So any bad grain, farmers, they tend to feed it to the cows, or buffaloes. Ultimately, that mycotoxin is coming to human body through in form of milk, ghee, butter, and that is still has the same risk as mycotoxin in any direct form. So it has a big benefit that if you reduce any quality-wise, insects, when they have, people still eat them because they don't have food enough. And you talk about your project that with fortifying, but if you reduce the insect damage, that means you don't need that much fortification. Otherwise, they take all the nutrition from the grain. People still feed to the animals or still consume the bad grain, and that has a big health problems in long term.
Great. Professor Singh, we see that now Professor Gajendra Singh has also joined.
Oh.
We would like to, sir, कुछ advice देंगे? We are discussing with Dr. Sevi Singh. He has given a very good, rather excellent presentation on smart grain storage. तो आपकी तरफ से कुछ सजेशन हो सर, प्रोफेसर गजेंद्र सिंह? I think आप म्यूट है सर, you are muted. I think perhaps he is not there. So,
any other question? Otherwise, people might be late for dinner.
It is already 10 o'clock.
Yes.
So there are no more questions in the chat box. Okay. So shall we conclude then? Okay.
Dr. Gajendra Singh ji, namaskar sir. Are you able to hear us? Professor Singh? I think he joined and maybe some connectivity issue.
Yes.
Anyway, let us conclude.
Okay. So I would now like to invite Ms. Sakshi Gupta for a formal vote of thanks.
Good evening to all my dear seniors. It gives me immense pleasure to propose vote of thanks for our 32 lecture of FCTL webinar series. I wholeheartedly thank our speaker, Dr. Chandra Singh sir, for sharing vast knowledge from scratch, like starting from a smart grain management system, then about cloud-based grain management system, how temperature, moisture, and
Sakshi, presentation for Thanksgiving slide. What is that?
Yes, I'm just presenting it. Yeah, Sakshi, just one moment. Are you able to see the presentation slide?
Yes.
Okay.
So like you shared vast knowledge from scratch, like starting from the smart grain management system, then you even shared about cloud-based grain management system, how temperature, moisture, and RH can be managed, and how only these three parameters can be so helpful for grain monitoring. How mathematical modeling can also be used for preventing the grain spoilage, and all these information you shared with incomparable patience. I even express my heartfelt gratitude to our mentor and coordinator, Professor N Mishra sir, for providing us this opportunity to gather knowledge in areas of expertise of seniors with the help of these webinar series platform. Finally, a big thanks to all our audience and all our seniors who found out time and participated enthusiastically in this webinar series and grace this session with their presence. We expect similar, or in fact even more and more responses for our coming lectures. In the end, once again, thank you everyone who directly or indirectly participated and gave their valuable presence for the success of this webinar. Thank you so much. Over to you, Anna sir.
Thank you very much.
Thank you very much. राकेश कुमार का, राकेश रायगर है क्या? ठीक है.
Okay. Thank you, sir. Yeah, thanks for the opportunity, and thank you everyone for joining my presentation and your time.
Thank you.
Thanks
sir.
a lot.
Thank you,
and
sir.
if you have any question or any ideas that you have research idea, either through Professor Mishra or directly, you can reach out to me, and I'll try my best to respond to you with appropriate information.
Okay, bye-bye. Thank you. We'll be in touch. और थोड़ा वर्कआउट करो जो डिस्कस किया एक होम स्टोरेज के लिए, राइट?
Yes.
गुड सिस्टम डेवलप करो.
Yes, sir.
Okay. Thank you. Bye-bye.